Before Einstein's theory of general relativity, scientists imagined space as a stage set on which the action played out. Einstein's genius was to realize that space itself is an actor in the drama.
We tend to think of space as just the stuff around us, but it's actually kind of a thing. It has a physical component to it, like a fabric, like a sheet.
In empty space, light travels in a straight line. But place something massive like our sun on the fabric of space, and its immense gravity warps space. As light travels past the sun, its straight path curves.
So light bends, not because the light bends, but the space in which the light is traveling curves itself.
This is why our probe's trajectory is curving. The black hole's gravity is warping the fabric of space. Everything that travels through this curved space must follow a curved path, including light.
The amazing thing is that not only does gravity warp the light into the black hole, light coming from farther away gets bent around it. And so you could see this shimmering distortion in the stars in the background as a black hole moved in front. It would almost be like taking a piece of glass and moving it across the star field.
And it's not just space that the black hole is bending. Time is warping too.
So if we send a probe going into a black hole, from our point of view, we see it falling in, and we see it falling in more and more slowly because its clock is ticking slower and slower and slower. That's a bizarre concept, and it's really hard to wrap our brains around, but that is what the math and physics are telling us.
We experience time as hours, minutes, seconds. It seems straightforward. But time is relative. It changes depending upon where you are.
It seems to the viewer that this shot has a picture of a moment in time and a moment in space. But it's actually not a moment in space and a moment in time. It's spread out in space because there's some depth of field behind me, but it's also spread out in time because the light from the whiteboard behind me left the whiteboard a little bit earlier than the light from my face. So when you see an image, you're really seeing something that's spread out in space and time.
So when gravity distorts space, it also alters time. Change the amount of gravity you're experiencing, and time shifts too.
Time does not flow at the same rate everywhere in a gravitational field. The farther down you are into the gravity, the slower time goes. Now, we actually have clocks that are accurate enough today to tell the difference in time between being in the basement and being in the attic. That's really true. Time really goes faster in the attic than it does in the basement.
Spend a day at the top of the Empire State Building, and you'll be a few billionths of a second older than someone who stayed on the ground floor. That's because time runs more slowly closer to the Earth's mass, where gravity is stronger. The more gravity there is, the slower time runs.
The existence of mass and energy in space curves space. So right now, I'm curving space-time around me. And as you get to more and more massive objects, that curvature becomes greater and greater. So the Earth is curving space-time, the sun is curving space-time, and when you get to black holes, the curvature is incredibly extreme.
So extreme, it sends the probe traveling through time.
It's hard to wrap your mind around this concept of space-time and even of black holes. It's pretty insane.
If I'm near a black hole, video conferencing my mom on a computer, she would actually see me go, "Hi, Mom." But I would feel that my time is running normally, whereas she is acting weird, going,
"Oh my goodness, Max, I'm a little bit worried about you. You're just feeling so funny."
Get close to a black hole, and you really can go back to the future.
And if you go back, people would say, "Oh, you look so youthful. This was a rejuvenating vacation." I'd be like, yes, because my time slowed down.
As our probe travels closer to the black hole, gravity's grip increases. time is slowing, while the probe and the torrent of matter racing inwards is accelerating until it piles up in a vast luminous ring called an accretion disk. Gravity should send all this matter spiraling straight down the giant cosmic drain hole. But something is interfering with gravity. It's a force with enough power to overcome the strongest gravity in the galaxy and drag the probe into a tornado of twisted time and space. Between our probe and the black hole lies a cosmic kill zone. It's a disk of molten dust and gas, tens of millions of miles wide. And it threatens to rip the probe to shreds.
You've got this matter falling into a black hole. It forms a disk, and there's friction inside of this disk. Things are rubbing against each other. And the velocities are so huge that this disk becomes terribly hot, and it glows when it gets that hot. And so ironically, even though black holes are dark, as matter falls in, it can light up and be the most luminous objects we see in the universe.
As the probe falls into this seething disk of matter, something strange happens. It doesn't rip apart or plummet into the abyss. Instead, the probe joins the spinning disk of matter orbiting the black hole. What force keeps all this matter from being sucked down into the black hole?
Almost everything in the universe spins in some way or another. That is due to angular momentum, this tendency that once you get something spinning, it's going to stay spinning.
When you think of that classic example of an ice skater spinning on an ice rink, and as she draws her arms in, she begins to spin faster and faster. Think about the scale involved when you go from a giant star to a tiny, hyper-compressed black hole. That spin was sped up and sped up and sped up.
As the matter falls towards the black hole, it whirls around faster and faster, reaching astronomically high speeds. Traveling at close to light speed, the matter is spinning too fast to travel directly into the black hole.
For example, there's a very famous ride in fairs where you can be in a room and it starts spinning and you're pushed against the wall and the floor recedes, but you stay up, you don't slide down. That same effect can stop you from falling into a black hole.
Spin something fast enough, and centrifugal force overpowers gravity.
There's a sort of yin and yang tension between gravity trying to crush things and the centrifugal force of spin trying to blow things apart.
But a black hole doesn't just spin the matter around it, it spins space itself. Picture a dust devil. The swirling dust reveals the movement of the unseen wind. In the same way, the spinning matter around a black hole reveals the unseen movement of space-time. As the black hole spins, it creates a tornado of space and time.
Black holes are weird no matter how you look at them. Everything about them is just so strange. But I think the weirdest thing about them is the fact that they can drag space and time, that fabric, around with them, wrapping themselves in a cloak of the material of the universe itself.
General relativity tells us that any massive spinning object, even the Earth, should move the space-time around it in a process called frame dragging.
Now, when we go to the case of the extreme gravity of a black hole, when we talk about frame dragging, we're talking about a region where the space is actually being dragged so strongly that it's impossible to remain at rest there.
Our theoretical probe is spinning through twisted space and time.
Things will look very warped and distorted. And what you see in front of you might even, in fact, be in back of you. And much of our intuition for what's where would actually break down.